Welcome students to today's lecture in the course of nuclear astrophysics. Today is the 6th lecture in this course. I hope you got some idea about the objectives of this course of nuclear astrophysics. What did we discuss in the previous lecture? Let me provide a brief summary. The evidences for the nucleosynthesis, nucleosynthesis in stars. That is what I discussed in the last class. What are the evidences I have discussed? The discovery of technetium-99. The spectrum of technetium in the recorded spectrum, when one of the or some of the lines were designated as technetium, it has given a strong evidence that nuclear reactions are still taking place. Why so much importance to the discovery of technetium, which has changed the way researchers looked at the evolution of universe? Because no isotope of technetium is stable. All isotopes of technetium are unstable. So, if the elements were produced much earlier, then the half life, which is of the order of 10 to the power of 5 or 10 to the power of 6 years, which is nothing in front of cosmological scales, time scales. Even now in the present times we are able to detect them, means the half life is 10 to the power of 5 years. So, 1 lakh years, that means before 1 lakh years this element must have been produced. It is a very small amount of time. So, that shows that the synthesis of elements is continuous process within the stars and elements beyond iron. So, I am talking about the heavy elements, right. And another discovery, aluminum-26. Aluminum-27 is a stable isotope, we know. So, it does not fall into that category of no isotope of an element is stable. So, this is a different category. So, aluminum-26 and its decay scheme I have discussed in detail in the previous lecture. So, the discovery of gamma line from aluminum has also provided a strong evidence that synthesis of nuclei is a continuous process within the stars. In today's lecture, let me provide some more interesting evidences for nucleosynthesis. After that, I will discuss a few more selected general properties of the universe. So, what was the first general property I have been discussing? Elemental abundance curve, and as part of that elemental abundance curve, I have covered the content related to evidence of nucleosynthesis. And after all these elements like aluminum-26, technetium-99, they were discovered, which provided a strong support to the nucleosynthesis in stars. The general features of elemental abundance curve we have seen, right. But there are some more selected general properties of the universe. What are those? I will discuss in today's lecture, fine. But before that, some more evidences for nucleosynthesis in stars, fine. So, as a recap, as I already discussed that in the last class the discovery of aluminum and technetium were discussed, and more evidences for nucleosynthesis in stars I have to discuss. Then some more properties of the universe. So, when I say some more properties, what is the first property I have discussed? Elemental abundance curve, and these are the properties which are relevant for nuclear astrophysics mainly, alright. So, what are the other important direct evidences for nucleosynthesis, that is the formation of nucleides because of the reaction between two nuclei, which is happening continuously within the stars, that is called as nucleosynthesis, right. What is the third evidence after technetium-99, 26 aluminum? The third evidence is detection of neutrinos, and whatever neutrinos were observed, the site is either sun or mainly supernova. neutrinos from other parts of the universe have not yet been observed in a majority way. Okay. So, whatever neutrinos were detected, they were coming from either from sun or supernova. And what is supernova 1 or 2? Right now, I am not going into that. The main part you have to understand is the detection of neutrinos as the evidence for nucleosynthesis. How the detection of neutrinos is linked with the nucleosynthesis? We have to understand this, right. See, neutrinos are particles which does not interact via electromagnetically or strong nuclear force. So, it is extremely difficult to detect, is not it? What are the particles you are aware of when it comes to nuclear radiation? Of course, keep in mind the wave particle duality when I say radiation or particles. Gamma rays, they do not have charge, they do not have mass, but they are electromagnetic in nature and they undergo either photoelectric effect or Compton scattering or pair production mostly. So, gamma rays can be detected if you use a material whose which possess this probability for photoelectric effect, Compton scattering or pair production in a large manner. So, those materials which possess large probability for these three processes or one of these three processes can be used for the detection of gamma rays, and the outcome is mainly electron, because in the photoelectric effect gamma ray is knocking out mainly K shell electron which is just near to the nucleus, and this electron is playing role in the detection of gamma ray, because of which this electron has become a free electron. Compton scattering, there also some of the energy of the gamma ray is transferred to the loosely bound electron, and that has become free, which is undergoing scattering with some angle. Gamma ray is undergoing with some scattering with some angle and electron is undergoing some recoil. You detect this electron, and then pair production, gamma ray is depositing its energy in the presence of nuclear field. Then that energy is getting converted into electron and positron, pair production. So, this electron with a negative charge is becoming reason for the detection of gamma, whereas electron with positive charge, that is positron, will have a deal with the electron in its surroundings and it undergoes annihilation. So, because of annihilation, again 2 photons are coming out, and these photons will again undergo either photoelectric, Compton, of course not pair production, because 511 keV is much less than the pair production required energy. So, this is how gamma rays are detected. What about alpha particles? They have mass, they have charge, and they undergo Coulombic interaction. So, excitation, ionization take place. Beta rays, electrons, protons, irrespective of their charge, of course they have mass and some charge, either negative or positive. So, the presence of mass and charge allows the charged particles like electron, proton, alpha particles and heavy ions to get detected via Coulombic interaction. I hope all of you remember the basics of beta decay. So, when I say beta decay, it could be either beta minus or beta plus. And when one proton gets converted into neutron or one neutron gets converted into proton, what will happen? Either negatron, that is electron with negative charge, or positron, that means electron with positive charge will be emitted. Along with that, you are very well familiar that neutrinos are also emitted, right? And these neutrinos, they are the byproducts of large number of nuclear processes within the stars. Neutrinos, they are the byproducts of large number of nuclear processes. So, what? See, neutrinos, they also do not have any mass, they do not have any charge. Of course, lot of research is going on regarding its mass and charge. Right now, at this stage, you can assume that it has no charge and mass. At this stage, it is sufficient to understand. And they cannot undergo electromagnetic interaction like gamma, because gamma also does not have any charge or mass. So, neutrinos, because of their inability to participate in electromagnetic and or Coulombic interaction, it is extremely difficult to detect them. It is very difficult to detect them, because it is very difficult for the neutrinos to interact with the matter. Because the neutrinos cannot easily interact with the matter, from different parts of the star, when neutrinos are emitted, they cannot deposit their energy within the star, like alpha particles or some neutrons or protons, electrons, whatever nuclear radiation is emitted as part of the nuclear process, they can always deposit some energy. But neutrinos, they cannot, it is very difficult to interact with the matter, so they can easily escape from the star without any resistance. So, the neutrinos coming out from different parts of the universe, when researcher tried to detect them using some experimental setup, what is that I will show you. So, detection of neutrinos when it is possible, what does it mean? Nuclear processes are happening, and neutrinos detected, they also have given enough evidence. I am not going to the details, because the objective of the lecture of the in this nuclear astrophysics is to give you some kind of overview regarding the evidence of nucleosynthesis. Though in later part of the course, I will discuss some detailed physics aspects of the course. So, for time being, it is sufficient to believe, because enough research has been done in this regard. Neutrinos were detected on earth using some experimental facilities, and because the neutrinos were detected, we can say confidently that nuclear processes are happening continuously in the stars and different parts of the universe, okay? Though it is weakly interacting. Remember, neutrinos are the byproducts of the nuclear processes. Neutrinos are the byproducts of the neutrino processes, okay? Now, maybe you are aware of this. Every second, tens of billions of neutrinos are passing our body. Every second, tens of billions. We do not have any clue. Okay, so through my body, neutrons are passing. I do not have any, kind of feeling that neutrons are passing through me, because it hardly interacts with the matter. Okay, so many neutrinos are reaching Earth every second, and even through our body, in every second, tens of billions of neutrinos are passing through us. That is the reason the detection of neutrinos, because they cannot be detected so easily, the facilities are mainly on below the earth. Okay? So, the underground facilities are used to detect the neutrinos. Why underground? To get rid of background and cosmic rays. Okay? Because the kind of detector which is supposed to detect neutrinos, if the ability of the detection is dominated by the background, it is very difficult to separate the contribution of the background from the contribution of neutrinos. So, it is essential to go to a region where background is almost 0. So, either you prepare or you design a laboratory within, you make a big hole within a big hill and set up a laboratory there, because this hill will protect the facility from the background and cosmic rays, or you go to the underground. So, this is how neutrinos can be detected if we acquire the data for long time. All right. Now, this is one of the important facilities across the world, Kamiokande in Japan. It is 1 kilometer underground. The detection medium is ultra pure water, because to increase the ability, to increase the probability of detecting the neutrino, one has to go for very high quality detection medium, that is water. Why only water and all those things I will not discuss, because that is not the purpose of this lecture. Okay. The purpose of this slide is to show you how neutrinos have played an important role in establishing the fact that nuclear processes are still taking place. And the purpose of this Kamiokande facility in Japan is not only to detect the neutrinos, but also to look for decay of proton. Neutron decay is well known, right? Its half life is in minutes, of the order of minutes, and a free neutron can decay, giving rise to proton, but a free proton is almost stable. So, if you want to understand the decay of proton and the neutrino coming out from the proton, we need to use this kind of facility. This facility is also designed to detect the neutrinos from sun and the atmosphere. Not only that, it keeps an eye on the supernova in the Milky Way galaxy. So, this particular facility of Kamiyakonde in Japan is working to meet these three objectives: the studies of proton decay, the studies of neutrinos from sun and atmosphere, and the properties of the supernova. So, I took the liberty of discussing one important facility for the neutrino detection. More details can be found in the website of this facility. All right. Now, let me go for another important direct evidence for nucleosynthesis. After that, I will stop the discussion on evidence for nucleosynthesis. So, till now how many evidences I have discussed? Number 1, technetium discovery. Number 2, aluminum 26. Number 3, detection of neutrinos, which is very difficult to detect. The fourth evidence, which is the last one, is it looks like this. Okay. See, when researchers tries to model the supernova, the models predicted that during the explosion stage of star, nickel 56 is ejected. So, the ejection of 56 nickel, whose half life is say 6 days. Now, I am not discussing how people have measured this half life of this nickel, all those things, the details will be discussed later. Okay. So, the ejection of nickel 56, which is radioactive, leads to the leads to the formation of cobalt 56, See here, its half life is also 77 days, not like years or light years. It is 77 days, and this cobalt 56 is again radioactive. So, it tries to achieve the stable status. And by forming iron, finally the stability is reached. Fine, iron 56 is very stable. As I said, while modeling the supernova, it is important to consider the ejection of nickel 56, which is giving rise to cobalt 56, which is forming iron 56. Do you remember in periodic table up to calcium you might have memorized Fe, Co, Ni, Kunj. Okay? Fe, iris, cobalt, nickel, copper and zinc. Okay? Then you can, with this kind of thumb rules, you can also remember the elements and their atomic numbers up to 30. Okay? So, what is so important about this evidence? See, the detection of 3612 keV from cobalt 56. As I said, cobalt 56 is decaying to iron 56, and because of this transformation from cobalt 56 to iron 56, a gamma ray is emitted whose energy is 3612 keV. So, all this is only informative. Okay? Please understand whatever information is available, just I am providing, so that I want to convey a few direct evidences for the nucleosynthesis. Now, this detection of photons, that means gamma ray, okay, of energy 3.6 MeV from cobalt 56 has been detected. The photons of this energy have been detected. What is so special about it? You see, the decay of nickel 56 to cobalt 56 and then to iron 56. This decay decides the emission of light, which is found to be in good agreement with the light curves of the supernova. I am using a word light curve. Okay? So, basically when you draw luminosity, what is luminosity, my dear? Energy emitted per unit time. Okay? Joules per unit time, if you take some kind of unit for luminosity, then normally it looks like this. This is called as light curve. I am drawing one approximate light curve. Theoretically, when people have plotted, theoretically when people have calculated this kind of light curve, it required the presence of decay from nickel to cobalt, cobalt to iron. So what? See, the good agreement between the light curve calculated from theory and light curve measured, that good agreement provides a strong evidence that nucleosynthesis is continuous process in the stars. I hope it is a bit clear to you. By saying that a good agreement between the light curve calculated for supernova using theoretical models and measurements, and whatever concepts are included in the theoretical predictions, that is decay of nickel 56 to cobalt 56, and cobalt 56 is giving to 3 point something MeV, and then it is reaching to iron 56, provides a strong evidence that nucleosynthesis is continuous process within the stars. So, with this, let me close the discussion on evidences for nucleosynthesis. So, how many evidences I have discussed in lecture? Technetium, discovery of technetium, discovery of aluminum 26 because of their decay, whatever gamma rays emitted. So, when I said discovery of aluminum 26, not directly aluminum 26, the gamma ray emitted because of the aluminum 26. Similarly, for technetium. Neutrinos, that is the third evidence. Fourth one is the gamma ray whose energy is 3.6 MeV emitted by cobalt 56. Okay? And the cobalt 56 emits 3.6 MeV, means the formation of cobalt 56 is still taking place. That means synthesis of elements is going on continuously within the stars. So, I hope you got enough idea about the evidences for nucleosynthesis. So, as part of discussion on selected general properties of the universe, I have started discussing elemental abundance curve and how curve looks like, what are the important features of this curve. Then I discussed this list of evidences for nucleosynthesis. So, one property of the universe is over, and the second property which I would like to present here is following. Okay. So, I apologize. Before that, I want to discuss one more important thing in the course. I am using the word in the whole course, one of the most fascinating concept. Please try to understand this, and the detailed discussion on this particular topic will come after several lectures. Detailed mathematics will be done at that time. Right now, because I am discussing the elemental abundance curve and discovery of various elements, let me try to discuss one of the most fascinating concepts in the field of nuclear astrophysics. Okay? See this diagram. Number of protons on y axis, number of neutrons on x axis. You can see n is equal to z curve, it is a straight line, this is a straight line, fine. And can you see hydrogen 1, 2, 3, number of protons, okay, and number of neutrons on x axis. So, number of protons is only 1, number of neutrons is 0, 1 and 2. That makes mass number, the boxes contains numbers which are the mass number, fine. The sum of number of protons and neutrons is given inside the box. So, the specialty of this diagram, if you see, you can see the shaded diagram. The shaded one is stable isotope. I repeat, in the whole diagram, the shaded boxes denote stable isotopes. For example, hydrogen and deuterium, they are stable, tritium is not. Okay? Helium 3, helium 4, they are stable or almost stable. Okay? Alpha, of course, alpha particle is highly stable, there is no doubt about it. And lithium with mass number 6 and 7, they are stable, but not 8 and 9, that is why they are not shaded. Beryllium 7 and 8, they are not shaded, so they are unstable. Only 9 is stable, that is why the box is shaded. 10, 11, 12, they are not stable. What is so special about it? You can see stable isotopes with all mass numbers. See 1, 2, 3, 4. Where is 5? Keep looking for it. 6, 7, 8. 8 is also missing, right? 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There can be repetition, it is okay. And okay, 19, 20, 21, 22, 23, okay, 24, 25, 26, 27, 28, 29, 30. What is so special about it? The mass numbers 5 and 8, stable isotopes with mass numbers 5 and 8, they are not visible here. How nucleosynthesis could have been proceed without the existence of stable isotopes with mass numbers 5 and 8? That was a mystery for a long time to the researchers. See, synthesis of elements is happening one after the other. It is not like suddenly mass number 10 is giving rise to mass number 50. No, it is a step by step process, right? Now, let me discuss some salient features of this diagram. Why are there no stable isotopes with an atomic mass of 5 or 8? That is the question. That is the question. Why there is no stable isotope with mass number 8, 5 or and 8? Salpeter, a researcher, has suggested, okay, alpha plus alpha, when it gives rise to beryllium 8, which is highly unstable. You see in this box, beryllium 8 is unstable. So, when it is highly unstable, you know, its lifetime is also very, very less. Fine, 10 to the power of minus 12 seconds kind of lifetime. Immediately it undergoes decay into alpha and alpha. So, this beryllium, which is formed because of reaction between two alpha particles, is giving rise to a highly unstable beryllium 8, which again goes back to two alpha particles. But Salpeter suggested there is always some probability for this beryllium 8 to react with another alpha particle, even though it has very less lifetime. Of course, you can ask, on one hand I am saying beryllium half-life is lifetime is extremely less, picoseconds kind of thing. At the same time I am saying it can also react with alpha particle. Where is the time available? Time is available provided the transit time between the two particles, two alpha particles, is lesser than the lifetime of the beryllium 8. And when huge number of alpha particles are there in the star, before beryllium 8 undergoes a decay, this alpha particle can react with beryllium 8, giving rise to a stable element carbon 12. How it is addressing my question? Why there are mass numbers 5 and 8? See here. Okay. So, beryllium 8 plus alpha giving rise to carbon 12. All right. So, that is why this is called as triple alpha reaction. Even though it is triple alpha reaction, it is basically two step process. Number 1, alpha plus alpha is giving rise to beryllium 8. Number 2, beryllium 8 plus alpha is giving rise to carbon 12. Okay. Now, this reaction has been proved to be main energy source in red giant stars. Red giant stars. What are the red giant stars? I will discuss very soon. Just wait for some time. Then a researcher Hoyle predicted, for this prediction he won the Nobel Prize. Hoyle has predicted that the probability for alpha to react with beryllium 8 will be very less, is very less, and the resultant abundance of carbon 12 is not matching with the observed abundance. I repeat, whatever probability of the reaction people have assumed is not sufficient to reproduce the abundance of the carbon 12. Then Hoyle has predicted, fine, the rate of triple alpha reaction should be high, then only the calculated abundance can match with the observed abundance. For this to happen, he said that in carbon 12 there has to be an energy level whose energy is 7.7 MeV. That also its spin should be 0 and parity should be positive. Now, what is the spin and parity? as I said in one of the previous lectures, it is helpful to understand the course if you know the concept of shell model. If you are not aware of it, it is not very difficult to understand. Please go through the textbooks. So, liquid drop model you might be aware of. Whatever disadvantages in the liquid drop model are there, they have been addressed mostly using shell model, and if you know shell model, it is not a difficult thing for you to understand the concept of spin and parity of each energy level of the nucleus. See, so Hoyle has predicted that in carbon 12, if there is no 7.7 MeV state, then the probability for the capture will be extremely small, and it is not possible to match the calculated abundance with the observed abundance. Okay. So, because of the prediction of Hoyle, later it was experimentally confirmed that yes, indeed an energy, a level whose energy is 1.7 MeV exists in the decay scheme of carbon 12, and it is not very easy to determine the energy level of 7.7 MeV in carbon 12. Okay. So, this slide tells us the synthesis of elements having stable and unstable in nature, and what are the corresponding mass numbers. Because I have discussed technetium, aluminum 26 and nickel, cobalt and iron, I thought I should give some flavor about the triple alpha reaction, which is the energy source for one particular type of stars, that is red giant stars. Okay. So, hope you have understood how the bypass in nucleosynthesis could take place at mass numbers 5 and 8. So, even though there is no stable isotope having mass number 5 and 8, carbon 12 could be formed because of the triple alpha reaction. More details will be discussed in coming lectures. Thank you very much for your patience. Thank you.